Okay, link is in the chat. Okay, cool. So today we're going to be talking about crustal movement. And I'd like you to give an example of one of the plate boundaries that we discussed yesterday and include an image that illustrates its properties. There, Ethan, also transform boundary. You can see how it slides side to side. Gretch, I can't see your image. Jules got another subduction boundary, a convergent boundary. Very good, guys. Take another minute. The period. All right, today's aim. What evidence do we have for crustal movement? Originally I was going to have you guys do a Padlet, but I skipped that. We just did it in the Nearpod. Mini lesson evidence for crustal movement. We'll talk for about 15 minutes. Then you guys are going to jump back into your lab number 8. That's a web quest for plate tectonics. I'm asking that you try and just get page number 2 done. If you could do 2 and 3, that would help you out because that is due on Thursday. And being that today is Tuesday, if I got my days straight, yeah, you want to make sure that you're ready for everything else that's happening this week. We do have homework tonight, November 17, 2020 homework. That's what it's listed as in the Google Classroom. And also, we do have an earthquakes tectonic exam tomorrow. So please make sure you do that. Study for that. All right. So I'm going to throw out a question to you guys. Have you ever dug a hole in the ground? And if you did, what'd you notice? And if you didn't, take a look at the picture. Link is in the chat for those of you guys just joining us. It gets wet towards the bottom, absolutely. So the further you dig down, typically the closer you get to groundwater. Here in Canarsie, I think we're about 40 feet above sea level, so we don't typically get that much water here. You have to dig quite a ways down. What else do you notice? Take a look at the image. Well, the color starts to change. Yeah, Acacia. So what we're noticing here, if you look at the very top, we have that dark brown, almost black soil. Then you have like an orangey soil, then it's like lighter sand, then it gets dark again. So today's not a lesson about soil, but we do need to understand about the strata that makes up these soil horizons. Just like a horizon where the sky meets the ground, that's a horizon. It's basically the line that separates the two. We have one here. Now you can see here the horizons run A, B, C, D, and so on. One thing you might notice though is that you see that very top one, which says O, the O horizon, that's the organics. And organics is basically anything that was once alive that has died and decomposed. So most of soil, most of that dark layer is really broken down plants and animals. But we'll save that for another day. The one thing you do need to take away from this is the principle of original horizontality. Now, you know how like we have laws in science, what goes up must come down, right? Law of gravity. Well, we have laws in geology as well. And probably the most important one for us right now is sedimentary rocks are deposited in horizontal layers. So whenever you find rocks that are made up of small bits, they're going to be in those sideways horizontal layers. Now, if it's not horizontal, what does that mean? It means a movement has happened. So we're either looking at tilting, folding, or faulting. Here's an example of tilting, where you can see how the rocks are basically taken and shifted. Here's another example. Now, I want you to take a look at these. So this is folding. How could you bend rocks like that, really flex them? Because I know if you were to take a rock and you try to bend it yourself, it would either break or think about the same thing with glass. If you try to bend glass, it would break. What can you do to modify that substance so it can bend? Take a moment, think. Do to it is heat it up. Yeah, Grinch, you might think adding water to a substance would like make it more flexible, and that is true to a certain extent. You could probably flex it more, but it is heat and pressure. This rock right here went on a heck of a journey, really did. Now, we have fancy names for all this stuff. In fact, this one is called an anticline, and really all it is just an underground buried hill. Now this one looks like it's been burrowed out, like it's a cave or something. But generally, when we see these things, they're buried underground. They're hills or these waves like this. So like a plunging anticline would be a hill that's been buried, and a plunging syncline would be like a valley that's been buried. I mean, that's not exactly what it is. Really, it's just the rocks that are folded and then sometimes they're exposed. But it's probably best to think of them that way. Now, the cool thing about anticlines is anticlines can trap oil. They can trap valuable materials. So a lot of times we'll get it where we'll have a shale layer or a clay layer, which is made of a very, very fine particles. It's impermeable, where water or oil can't travel through it. And then you end up getting a reservoir of oil trapped underneath the rock. Now, as far as faults are concerned, this is a bit of a review. We have our normal faults and our reverse faults. If you remember, when you pull apart rock, they fall apart. Just like when I'm under stress. If I'm put under too much stress, I fall apart. Well, it's the same idea. As you pull things, they're going to drop. One's going to drop, the other one will probably remain the same. You don't have to worry about all this anatomy on here, like fault scarp and fault plane. Just understand it looks like this when they pull apart. Here's a reverse fault. It's when two rocks or two plates get pushed together. One starts to override the other. And then we have our transform fault. Now, our transform fault, very popular in California. We have a lot of them running through there. It's not the only place in the world where we have these. In fact, they are relatively common, but they're not all that common on the continental shelf or on the continental slopes. So where people live, right? Most of the ones that we see there are convergent or divergent. Now, here you can see where the fault is. I put a red line running through it. Same thing here. You can see how part of the wall moved towards us, part of it moved away. I highlighted this one with a red line as well. It's a fault running through those mountains. But it's not just faults that are evidence that rocks have moved. We could use things like displaced marine fossils. So marine means ocean, and a fossil is just an imprint of what was left behind. So here we see a bunch of bones from a fish that died 200 million years ago, or whatever. Now, you might expect to dig a hole by the ocean and to find fish bones, to find fossils. But we actually find these things all over the place. And in particular, we find them on mountains, which makes almost no sense, right? You would think the last place you're going to find a fish fossil would be on a mountain. But actually, that's one of the most common places to find it. And that is because uplift. The rocks that were on the bottom of the ocean floor between India and Asia, when those two continents collided, got uplifted and got pushed up. And that's why at the top of Mount Everest, we find fish bones. But along with those fish bones, we find other things that you might only expect to find down very low elevations, like, for example, beaches. How could you have a beach on top of a mountain? Well, 50 million years ago, it was a beach at the water. And then the uplift carried it up, leaving behind the sand, the sandstone, the limestone that you would find out in the coral reefs. All that stuff stays behind, and it's left as a beach on the side of a mountain. And lastly, what is the driving force behind these? We spoke about earlier in the year about convection currents. And in particular, here we have a convection current or large convection currents within the asthenosphere. So the asthenosphere also known as the plastic mantle, is part of the Earth's layers just below the surface, just below the crust, and it's got a lot of heat in it. And those high energy, high heat melted rock are pushing around, goes to that area known as the rift, and it starts to pull apart those plates. All right, we have a short one is an open-ended question. Provide a list of examples why soil horizons, anticlines, synclines, and in fact, I'm going to add more to this, faults, folds, and tilts. Why are all those things important to builders and to public safety?